It's a great pleasure to introduce Lev Birbrair, professor of the Federal University of Ceará, and he will speak about two normally embedded Hölder triangles, pizza and beyond. Lev, you can start.
Happy just in the beginning, I'm extremely happy to speak here because this seminar in San Carlos, really that it's it's a great honor to give a talk in San Carlos, because just because of the San Carlos school we really exist, that the singularity group in all Brazil is somehow very it's centered in San Carlos, and then we have something like wings of the San Carlos group, and one of the wings is the Fortaleza wing, and but this is not really a unique one, and I'm very happy that there are several wings now. That you know, as the usual dragons, we don't have only two wings, we have plenty of wings. And then I don't speak about the heads, you see that. But now it's somehow very important thing that we have we are somehow unified, right? And then we can really, this is the probably the unique good thing that we just actually learned from the coronavirus, that we can have the online seminars and be together, even not being together, and just being in the several different places. Okay, so this is these are my words, and since I'm a first speaker, that I'm extremely happy just to be a person who is somehow who is opening this seminar. Okay, and then I will speak about Lipschitz geometry. That really it's my usual subject. It's my usual subject, and I would be happy just to be understandable, but somehow I will be slightly technical today. Not only understandable, but the technicality I would be really, you know, I will really try to make it as simple as possible. So that let's start from the following: that what is the Lipschitz geometry? What is the Lipschitz geometry? And what I'm going to speak is the Lipschitz geometry of germs of real surfaces, right? So the first point that, in fact, there are three Lipschitz geometries that we are concentrating. Just one is the inner Lipschitz geometry, another one is the outer, and the third one is ambient, that we don't touch today, right? We will speak the inner geometry. I probably was already sufficiently boring for all of you, explaining the inner Lipschitz geometry, and now I will speak about the outer Lipschitz geometry. Basically, the first step of the outer Lipschitz geometry, that should be, you hear me, right? And you see the slides, right? Hello?
Yeah, yes.
Yeah, okay, good. So that I will speak about the outer Lipschitz geometry. And then, just before starting, how do we make outer Lipschitz geometry? That first of all, we have the inner one, right? And you know that for the inner Lipschitz geometry is quite well understood. It's quite well understood. And then you see what I will be talking about. I'm talking about, let's say, or semi-algebraic germs of surfaces. I mean, by the surfaces, I mean the semi-algebraic germs of dimension 2. And it doesn't matter where they do live. they can live in quite high dimensional space, but my only point is that they have, so the surface germ is a germ of two-dimensional semi-algebraic or definable or subanalytic, but actually, let's also suppose that I'm talking about semi-algebraic things, right? And then you have the definition of equivalence, okay? The two surface germs X and Y are outer or inner by Lipschitz equivalent if there is an outer or inner by Lipschitz homeomorphism who sends first germ to another one, okay? And then just as usual, how the classification theorems are going on, I simply subdivide and I make a partition of a germ of the surface into so-called standard Hilbert triangles. So actually, I make a triangulation in such a way that all the triangle is Lipschitz normally embedded, or LNE. Just I come back to the definition of L and E sets, that if the two metrics, inner and outer, are by Lipschitz equivalent, okay? So then when I start from that, I'm coming to the partition. So I partition my germ into the triangles, which makes a triangulation. And this triangulation is just made by the normally embedded Hilbert triangles, okay? So this is the first step, and I make a partition into normally embedded Hilbert triangles, and just somehow I also have somehow canonical partition. I have somehow canonical partition that I won't describe, but it will be, but I always have this. It's not the minimal partition, but there is a sort of canonical partition, and it is the existence of this partition follows from the work of Andrei Gabrielov and Emmanuel Souza, who was our joint student. Okay, so that suppose we have a canonical partition into normally embedded Hilbert triangles, and is it enough? And this was the first question. And actually, when we were thinking about that in the beginning, it's in fact what I'm talking about is a big joint project with Alexandre Fernandez, Andrei Gabrielov, and Rodrigo Mendes. That actually, when we made this kind of partition, we thought that, okay, then we mainly know what actually happens. That basically we were sure that if you have a pair of normally embedded Hilbert triangles, then this pair is outer by Lipschitz equivalent to the union of the one of the triangle and then the distance function. And what I want to talk about today is that this is totally wrong, and that the outer Lipschitz geometry of these pairs, yes, pairs of normally embedded Hilbert triangles. Just you see, it's the simplest thing that you can imagine, that just two things like this, these two things like this, as in this picture, that are situated somehow in some space. And I want to see what happens with outer geometry of these pairs. And the conclusion is that this geometry is surprisingly non-trivial. And this is totally wrong, that one is a the pair is the triangle and the distance function, the graph of the distance function. No. What is our goal? Our goal is just to understand this geometry of this part of the pair of beta. We suppose that they have the same beta, right? The exponent, let me come back again to the picture. The beta is this exponent of Hilbert triangle that is bigger or equal than 1. So then our goal is just to create a discrete invariant such that these pairs are, so you take one pair and you take another pair, that they are outer by Lipschitz equivalent if and only if these discrete invariants are the same, right?
Lev, I'm a bit lost. By pair, what do you mean? You mean that you take the product?
Union, I mean the union of two normally embedded Hilbert triangles.
But it's a disjoint union. It's I don't see what you mean.
I have one triangle like this, and I have another triangle like this. That's it.
Mm-hmm.
Okay, and I suppose that they have the same vertex.
Okay.
I always suppose that they have this. I'm sorry, that this is this is how we make pictures. So that, and you will probably, it's the last two-dimensional picture that you see. And then also, I will be making one-dimensional pictures as usual, and my one-dimensional pictures will present the links. So what does it mean? The link of a surface which contains is obtained as a union of two Hilbert triangles, and this surface. So suppose they intersect only in the singular point. Okay.
Another question is, when you speak about partitions in surfaces, you need to identify beholder triangles with the member of the partitions, and yes, this identification should be what? Be Lipschitz?
So
what is the definitions of a partition?
Suppose you have a local triangulation, right?
Mm-hmm.
This partition is a local triangulation, and the theorem is that there is a local triangulation such that each Hilbert triangle of each triangle of this local triangulation is by Lipschitz equivalent to this one for some different betas.
Thank you.
Okay, this is and this partition brings you an inner by Lipschitz invariant. Okay. And now I make the situation more difficult because I'm talking about the outer classification and not about the inner. So that I would be happy to have questions now. If if somebody doesn't understand something, I would like you to ask the question now. Okay? Because Kevin did very well that if something was not clear, just let me clarify it as soon as possible. Other questions?
Don't be shy, if you have questions.
Yeah, don't be shy.
So do you suppose that beta is a rational number, right?
It's a rational number bigger or equal than 1.
Okay, thank you.
So that the point is, again, I have a partition into the pieces like this, right? And now I just take two pieces like this, and I want to classify them from the outer by Lipschitz viewpoint. Okay? It's okay, Maria Aparecida, Sidinia. Okay, right?
Sure, very clear.
I wanted you to ask the question because it's very, very much related to our joint work.
Yeah.
It's quite related to our joint work on the just on the graphs of Lipschitz functions, and I will talk about that later, just in few words. Okay, so we have these things, and then we have our work that first of all the work with Siginia, João Carlos, and Alexandre, and the next work with Alexandre, Andrei, and Vincent Grandjean, where we really studied very particular case of the surfaces, where the surface is just a plane, two-dimensional plane, and a graph of some polynomial function. And actually, in this case, we understand everything, right? And so let me, and this goal is actually completed in the paper with Andrei, Alexandre, and Vincent. Okay, but this is an example that I will come to this example several times. I will come to this example several times, and you just see that here you have, by the way, what I will be drawing. I will be drawing the links, so the intersections of my pairs with these small spheres, okay? So this is a one-dimensional picture, and who are these q's? Q's and mu's are the numbers that corresponds to the velocities, how these stories are, how these things are vanishing when we go farther, closer and closer to the singularity. So we have the vanishing grades, and all of these are vanishing grades. So that if you want to see this picture is actually two-dimensional. And this is the section of this picture, and you will see that if you just consider the distance function, then the distance function doesn't see what is above. The distance function only sees what is below, and distance function sees nothing what happens here. And moreover, the orientation is quite changed. Okay, the orientation is quite changed, and you see that it cannot be by Lipschitz equivalent to the triangle below and the graph of the distance function. So, but this picture you can really have in the Lipschitz geometry of the pairs of Hilbert triangles, right? Then, so, and this somehow shows that this story is surprisingly non-trivial, and you can imagine that in this thing you can make a tail that will exist, will behave something like this, and the point what I want to explain now, just I try to define a tool that will allow me to make this kind of invariant. It's okay, Alexandre, you have a question or not?
No question.
No question, so it's clear for you, right? Okay,
Right.
Thank you. Then, okay, now let me define the tools. So that what is an arc in a surface? It's a germ of the map, gamma, defined on, let's say, semi-algebraic always. It's a germ of a map from 0 to epsilon to x, and we suppose that the arc is parameterized by the distance to the origin. Okay, so this is a germ of the arc. Then the valid link. So there is a very nice and very clever French-Polish mathematician called Guillaume Valette, and he produced so-called Valette link as the space of all the arcs on X, and we suppose that all the arcs are parameterized by the distance to their origin. So that, just don't mix it to the Fukui invariant, where he just was talking about the space of all the analytic arcs. No, I'm talking about the semi-algebraic arcs, and in such a way that they are parameterized by the distance to the origin. And then we have the tangency order of the two arcs, gamma and gamma prime, defined as it is written. We just parameterize both of them. We parameterize both of them. I'm sorry, I have to disconnect this stupid phone. And then because he will not allow me to talk. And then the tangency order, I just take a semi-algebraic function depending on t, just gamma of t minus gamma prime of t. Then you have, by the Puiseux decomposition, you have this as c times t to the k, where k is a rational number in this case. And if we speak about a minimal structure, then it's an element of the exponent fields of the minimal structure. So that's c times t to the k, and this is plus higher order terms that we always ignore. So this k is nobody else as their tangency order, tort. And then we define a tort of arc to some subset as just as the supremo of the torts for all the arcs belonging to the Valette link of the subset. So the tangency order actually defines a non-Archimedean metric on the Valette link, right? And then, just recently it became popular, especially in the lectures of Patrick Popescu-Pompou, that he was somehow just always interesting how to relate the non-Archimedean fields with their singularity theory. And this is one of the examples, okay? So that we have the tangency order, and the tangency order defines a non-Archimedean metric. Okay? Just, we are talking about non-singular arcs. That arc is called non-singular if it actually lives in some Hilbert triangle, some normally embedded Hilbert triangle. It lives as interior. It lives as an interior arc in some normally embedded Hilbert triangle. And Hilbert triangle is called non-singular if its interior doesn't have their non-singular arcs. Okay, so that we have just now we consider the pairs of normally embedded and non-singular Hilbert triangles. Okay, then we have this triangle, and let's start to study what is happening in the Valette link of it. So we have a surface geom, and we define a zone. We define a zone, just a zone there is a subset that it's a subset if you have any two arcs on this subset, then the Hilbert triangle bounded these two arcs also lives in this subset. So that their definition is somehow connectedness in the terms of the Hilbert triangle. That actually it's somehow a stupid thing, because this valid link is somehow totally disconnected. But actually we have some analog of the things to be just arcwise connected. Okay, so the germ is a subset. A zone is a subset of the germ, which is, it's not necessarily a Hilbert triangle. It's maybe not at all. But the point is that if you have any two arcs in the zone, then the Hilbert triangle bounded by these two arcs, that I will have the notation T gamma gamma prime. Now, this is a Hilbert triangle. Let me come back again to the picture. Let me come back on the picture of the Hilbert triangle. That you can imagine that this is a triangle. Here it's gamma prime, right? And it could be curvilinear. It's much more curvilinear than it is here, right? And then, so this is the Hilbert triangle bounded by the two arcs, right? And this is called a zone. And what is the order of the zone? The order of the zone is the infimum of all the chords, all the tangency orders of any two arcs who live in the zone.
Left is in general, if you have a concrete surface gem singularity, so with given by equations,
yes.
is it simple to describe what is valid links and the zone?
No, but just the valid link, just take all the semi-algebraic arcs who live in this Hilbert triangle.
So this means it's some kind of Puisieux series or something?
Yeah, it's sort of the Puisieux series, but that it's just, you don't mix it with the Foucault invariant, that just something like, because this is the set of all the arcs, but what I'm what I impose that they should be parameterized by the order to by the distance to the singular point. Okay. Okay. Could I continue?
Yes. Yes.
Do you see my slides now again? Hello,
yeah,
Kevin.
Yeah. Yes. Yes.
Okay. Then you have a singular zone is just an arc, and we say the order of the singular zone is infinity. And then who is the generic arc? The generic arc is an arc such that from the right hand and from the left hand of this arc, there is another arc such that toward the tangency order equals to beta, right? And a zone is called perfect, that for any arc who lives in there is a Hilbert triangle such that I'm sorry, that actually it means that the zone is called perfect if all the arcs there are generic. So it means that it doesn't matter for you which arc to choose. Okay, these are, so that just I stand on that a little bit more than, because this is the tool. The zone language is a tool how we are going to describe the geometry. Okay, now the special case called pizza. So that you have a Hilbert triangle on XY plane, and we have a non-negative Lipschitz function on this T, such that this function is equals to 0 at 0. And then the second triangle, T prime, is the graph of this function. As I told you that this thing we can describe totally. So how we do that? How do we do that? We for each arc in the valid link in T, we define the order of the function f on this triangle. What does it mean? That we just it's the this function is a function on T, and we take the piezo, and then we have the first piezo exponent. Okay, and we say that Q of T is the set of piezo exponent, and actually the set of the piezo exponent defined on the interval, right? On our triangle, and that triangle, actually the set of the piezo exponent is always a closed interval in the field of exponent, including infinity. Okay, then T is called elementary if for any Q we define the set ZQ, right? ZQ is the set of all the arcs who has the same order. That's the arcs defined on the T such that the order is equal to Q. Okay? And we say that our triangle is elementary if the Q zone is a zone. Okay? Because actually the Q zone doesn't have to be a zone. For some functions basically for the majority of the functions, this shouldn't be a zone, right? But sometimes it can be a zone. And this is the case where this thing is a zone, okay? And then we define the width function. We define the width function on the set of the exponents of this triangle. It's the function just defined on the Q, so that the triangle should be elementary if you want the width function to be defined. And we define is as follows, that mu of Q is the order of the Q zone. So, and there another definition that this triangle is a pizza slice if this width function is defined and it is affine. And what is a pizza? Pizza is here it's the partition. I will come back to this picture. The pizza associated non-negative Lipschitz function, it's a finite decomposition of the pizza slices. It's a finite decomposition of the pizza slices, and then we have the pizza toppings who are exponents of this triangle. Then the closed intervals who is just responsible for all the orders of the function on the on each triangle, and then on each thing we have a width function. And also we have a supporting arc, but I don't want just to fix your attention to the supporting arc. And the pizza is called minimum if the adjacent pizza slices, the union of adjacent pizza slices is not a pizza slice. Okay? If the union of the adjacent pizza slices is not a pizza slice. Okay? So then here we have the somehow the picture of the pizza for this function. Let me just, maybe if I will have the special lecture just devoted to the pizza, then I could describe in more details how do you define how you make a pizza. And then you have a theorem of just joint theorem with Alexandre Fernandez, Andrei Gabrielov, and Vincent Grandjean. The theorem is formulated like this: pizza exists. Okay, so the theorem says the pizza exists. And moreover, more than it exists, the pizza is just a discrete invariant. It's a discrete invariant, and this discrete invariant describe completely this kind of the situation. Describes completely this situation where one triangle is a triangle on the plane, and another one is I'm sorry, I have a lecture. I have a lecture now, and that I'm sorry, I cannot. I thought I disconnected my phone. I didn't. Okay, so that this thing is actually describes the situation of the situation where where one function is
there is a problem with the beamer. I cannot see the beamer anymore.
Okay, let me. Now, do you see it or not?
Yeah, yes.
Now you see. Okay, very good.
The invariant of the pizza is attached to graph of.
This is the complete invariant in the case where one triangle is just a plain triangle and another triangle is the graph of some Lipschitz function. So we have somehow a canonical partition into the elementary triangles, and then we have who are the pizza slices. Okay. So this is this is the situation where we understand perfectly what's happening. So what is beyond? Well, okay. Actually, this somehow I will skip this what I prepared about canonicity of pizza. The canonicity of pizza, that actually pizza is canonical, but it's not unique. You have some freedom to put their boundary arcs, but actually this freedom is not a big deal, because it actually means that any arc like this lives in some perfect zone. So that for pizza, you have just a partition into this kind of elementary triangles where you have this well-defined bits functions, but the boundary are not fixed. The boundaries, or probably they are fixed if they belong to the zero set, right? But generally, they are not necessary in the zero set. Okay. Do you see everything now? Okay, good. Now we are going to come to the just to the subject of my talk, so that we are not in this special case. We are in the case where one Hilder triangle and another are somehow a normal pair, right? they are normal pairs. It means that they are normally embedded both. They have the same they have the same exponents, and moreover, for all the boundary arcs, the distance to another triangle, that's at the order or to another triangle, is just realized in a boundary arc. So this means that we have a normal pair. So that you have two, let me come back again to the picture of pair of triangles here. So that the distance of this arc, so here a point is an arc, right? So the distance of this one to the another triangle is just realized in the boundary arc, and here the distance to another is also realized in the boundary arc. Okay? So what's happening then? First of all, the question, how we come back to the case, how we just identify the case where we have a pizza, where the pizza just describes the geometry completely. And the pizza describes the geometry completely if one triangle is elementary with respect to the distance function. So that, and another one is also elementary with respect to the another distance function. But in this case, we have that just the previous situation, that this pair is just described by their pizza, right? But it is not always okay. There are plenty of the another examples, and let me come slightly further for the examples. So that come here, and here you will see again that you saw this picture, and here there are so-called maximum zones, right? And here there are, what is here? There are so-called maximum zones, so that the zones of the arc who has the locally maximal contact to the another triangle. And actually what happens that, what actually happens, that I will just go a little bit quicker, then we have the zones of maximal exponents. The zones of maximal exponents is the zone of the arcs such that the exponent of the distance function to another triangle has a more local maximum. Okay? And then what we, so here is the formal definition of the maximal exponent zone. It means that you are in a zone where you have arcs with the locally maximal exponent, and if you go to the left and go to the right, then these zones, then the exponent decreases. Then the exponent just slightly decreases. So just somehow the analog of the maximums, of the local maximums of functions, but in terms of the valid lengths. So what actually happens? Then there is a theorem. The theorem, we consider the set of all the locally maximum exponent zones in the first triangle and in the second, right? And then the theorem is that the number of the this kind of maximum zones in the first triangle and the maximum zones in the second triangle is the same. And actually, if we orient these two triangles, and then we have the set or the sequence that 1, 2, and somehow m. There will be the set of the maximum zones on the first triangle, and what is the point is that there is a one-to-one correspondence of the set of the maximum zones on the first triangle and the set of the maximum zones in the second triangle. But this map, it doesn't really do not preserves the orientation. It preserves, it's just a permutation. So that this sigma is a permutation of the locally exponent zones on the first one, and just here we have we also count 1, 2, 3, 4, and according to here we have 1, 3, 2, 4. So this is the permutation that we just interchanged the orders of the interior maximum zones. Okay. So then you have, and actually this is the first part of the invariant. The first part of the invariant is a permutation of the set of the local maximum zones. Okay. So that this sigma, this will just leave a part of the pizza, and this is a permutation of the set of the local maximum zones. Let me go further, and that it's one the permutation, and actually we have transversal zones. What is a transversal zone? So suppose you have, and who are the transversal triangles? So because they say that two triangles are transversal, if they leave, if one can find another Hilbert triangle such that both will live over there, and the this one is also normally embedded in Hilbert triangle. So then we have, let me show in my previous examples who are transversal. For instance, if you take this one, this Hilbert triangle, okay, over here, and we take this one, just the last one in the triangle below, and the first one in the triangle above, and these are transversal. So that they are transversal if they live in the same plane. They are transversal if they are actually transversal. But the important thing is just not to be just very non-transversal, right? So that we have the transversal pair and we have non-transversal pair. And the point is that we consider also the pizza decomposition. We consider a pizza decomposition of the distance function, right? And we consider the pizza slices corresponding to such that the triangles on the decomposition below and then in composition above will be highly non-transversal. So we make a decomposition, we take the pizza slices, and then we have the pizza slices corresponding to the non-transversal pairs. And another observation and another theorem is that here we also have a permutation. We have a permutation of the maximum zones, and we have a permutation of the non-transversal pizza slices. So that actually we have a pair of permutations, sigma and tau. And what we can prove that actually if the pairs are if the pairs are by Lipschitz equivalent, then the permutation sigma and tau and all the pizza toppings are invariant. And let me finish my talk by the conjecture that the norm, not this one, but this one, that if we have the normal pairs of the triangles, if we have the same pizzas of the distance functions, and we have the same two permutations, the permutations of the permutation of the maximal pizza zone and the permutation of the non-transversal pizza slices. And if we have this and this and this, then we get that we have the by Lipschitz equivalent of pairs. But this is still a conjecture, and we are in the process of the proving of this conjecture. So thank you for your attention.